All right, so what you read there at the top of worksheet 2 was just a different version of the second fundamental theorem of calculus. Um, I think that calculus people think they're being clever by messing with the notation, and I think that they think that's forcing students to really understand the theory so that the notation doesn't matter. I, I don't think they're right, because the whole reason we come up with standard notations for things is to make it easier to understand, right? I mean, when you're working a problem, capital A means area in one problem. Every time you find an area, you always use capital A. So we standardize things so that you don't have to worry about the notation, so that you can concentrate on the theory. Whereas in calculus, they seem to take a different up the notation, and we'll call the derivative little f this time, and the function f and the derivative f prime. Then we'll switch to g, and I don't. They think they're forcing you to understand the theory. I think they're making it harder to understand the theory by never standardizing the notation. They write books and get published and make money. I'm stuck here teaching you guys. So I guess they're the ones that know what they're talking about. But it does make it more difficult, okay? So, they've worded it differently than our book has worded it, and our book's probably a little different than somebody else. I'm sure each author changes something just a bit so that they're not accused of plagiarism, okay? So it's not standard, but the idea is still the same. So once we cut through the meat of it, let's work a couple of examples, and I think you'll remember how the second fundamental theorem of calculus works. So they want us to, well, they do this in 2 steps. So if we look at number 1 here on the first page of this worksheet, all right, it says, step 1, given f of t, evaluate capital F of x equals the integral from 1 to x of f of t dt to find capital F of x in terms of x. And then step 2, we'll read that in a minute. So we have our function defined as an integral, okay? And they want us to find capital F of x in terms of x, meaning find capital F of x as a regular function, not a function of an integral, or not an integral function, okay? So no more integral sign. So that's what we're going to do here on number 1. So this is number 1. This will be step 1, okay? Capital F of x equals integral from 1 to x of f of t dt. And they tell us for this particular problem that f of t is t cubed. So capital F of x equals the integral from 1 to x of t cubed dt. All right? Well, we've done this kind of thing 100 times. So we take the antiderivative. That'll be 1/4 t to the 4th. We evaluate from 1 to x. And so that's still what capital F of x equals. Now evaluate. So you evaluate for the x first. That'd be 1/4 x to the 4th minus, then you evaluate for the 1. 1/4 times 1 to the 4th is 1/4. So that's what capital F of x equals. Now, take the derivative of this result to find capital F prime of x. So, step 2. We've got capital F of x equals 1/4 x to the 4th minus 1/4. We need to find capital F prime of x. Well, what's the derivative of 1/4 x to the 4th? X cubed. What's the derivative of negative 1/4? 0. Okay? So, what have we proven here? Well, not proven. We've given an example of the second fundamental theorem of calculus. Okay? If we're given f of x, capital F of x, equals the integral from a constant to x of f of t dt, then capital F of x equals f, little f, with an x instead of a t. Okay? So that's what we've done here. Does that ring a bell? Remember doing that? And we did a bunch of those, right? And they're going to be on the AP test, so we're going to do a bunch again so that we get good at it again. Because we'd finally gotten pretty good at it, I think. So we can do those. And they'll have you do it both ways. I mean, it's one of those things where even though we know the result, our book does it, this worksheet does it, it may show up on the AP test where you have to show them that it does work out that way. Okay? Let's skip ahead a few problems. Let's go to number 4. So, let us consider the even more difficult case of capital F of x equals the integral from 1 to x squared of f of t dt. So on this one, we're going to have to, the short version, the second fundamental theorem of calculus requires us to chain rule it. But they still want us to do the same idea. So it says, given little f of t, evaluate capital F of x equals the integral from 1 to x squared of f of t dt to find capital F of x as a function that doesn't have an integral in it. Then we'll take the derivative of that. So, here we go. We've got capital F of x equals the integral from 1 to x squared of f of t dt. We know that f of t is t cubed. That means, for step 1 here, that capital F of x equals the integral from 1 to x squared of t cubed dt. Okay, so let's take the integral. Capital F of x equals, well, the antiderivative of t cubed is still 1/4 t to the 4th, like it was 2 minutes ago. But this time it's not evaluated from 1 to x, it's evaluated from 1 to x squared. So let's evaluate for x squared first. So capital F of x equals 1/4 times x squared to the 4th minus, then let's evaluate for 1, which will be 1/4 times 1 to the 4th. 1/4 times 1 is 1/4. And x squared to the 4th, what's a better version of that? Yeah, x to the 8th. So we got capital F of x equals 1/4 x to the 8th minus 1/4. All right, that's step 1. We've written capital F of x without the integral in it. Step 2, take the derivative to find capital F prime of x. Well, power rule, 8 times 1/4 is 2, x, subtract 1 from the exponent, so now it's an x to the 7th. The derivative of negative 1/4 is 0. Oh, that's it, isn't it? That's our answer. 2x to the 7th. Now, remember this, that our second fundamental theorem of calculus says this. It says that if capital F of x equals the integral from a to u of f of t dt, then the derivative, and you can write the derivative different ways, right? We could say that the derivative of capital F with respect to x, we can just say capital F prime of x. But the derivative equals, oh, how did my equals end up down there? Equals the derivative of capital F with respect to u times the derivative of u with respect to x. Better yet, the derivative of capital F with respect to u, f of u, and then it's times the derivative of u. All right, so remember that? F of u times the derivative of u. So how would the second fundamental theorem of calculus apply to this problem? If I've got, let's switch colors here. If I've got capital F of x equals the integral from 1 to x squared of f of t dt, I should get little f of u times the derivative of u. Wait a minute. Let me just erase it here. I didn't mean to write f of t. I meant to write tq because that's what f of t is. Okay? So f of u. Replace the t with u. X squared cubed, and then times the derivative of u. Well, what's the derivative of x squared? 2x. Will we get the same result? That's x to the 6th times 2x. That's 2x to the 7th. So, when wrong telling us, right? But as they get more complicated, you're going to want to remember that second fundamental theorem of calculus. So, it's on the handout I gave you yesterday, the fundamental theorem of calculus, both parts there, part 1, part 2, first fundamental theorem, second fundamental theorem. You've got to know those. The first fundamental theorem we use all the time. That's the one we use when we evaluate a definite integral. Okay? But that second fundamental theorem of calculus that says that when you have a function defined as an integral, that the derivative of that turns out to be little f of u times the derivative of u, that's the one we got to get good at again. Okay? You guys with me? Okay. Now, if you look further down your worksheet, when you get to 7, 8, and 9, then you don't have to do the 2 steps, do you? You get to do the second fundamental theorem of calculus. 7, I don't think you'll find all that difficult. 8 and 9, the notation may be a challenge. Okay? You're not going to get nice little number answers for those. All right? Any questions so far? Okay, what I want to do then, at this point, is back up to worksheet 1. And which of these would you like to go over? Number 5. All right, on number 5, capital F of x equals the integral from 0 to x of f of t dt, where the graph of f is shown. So the graph of little f is shown. Now, let's not kid ourselves. Capital F and little f, what are they to each other? Little f is the what of capital F? It's the derivative, isn't it? Okay? You need to recognize that. This is one way the AP test people tell you that something is a derivative, is by defining it with a function like that. Okay? They're telling you that little f is the derivative of big F. This worksheet's not really, okay? But when you see that exact same thing further on down the road, that's what it's telling you. So keep that in mind. All right, so the graph of little f is shown at the right. So we got that. Now we need to fill in our chart. Okay? So first, they want x to be 0. Well, look, if I've got an integral from 0 to 0, there's nothing there. So there's no area, right? Now, they want us to do x equals 1. So look, all I'm doing is I'm just taking this, and I'm just going to replace the x with what they tell me for each one of these. So now it's a 1. Well, that means that's the integral from 0 to 1. The integral from 0 to 1 represents the area from 0 to 1. Sort of, because this whole region's underneath the graph, or underneath the x-axis, I mean. So we're not going to get the actual area. What are we going to get? We're going to get the signed area. We're going to get a negative, aren't we? Okay? So that's a triangle, 1/2 base times height. So 1/2 times a base of 1 times a height that goes down 2. So 1/2 times 1 times 2 is 1, but it's a negative 1 because the entire region's below the x-axis. All right? Then we do the same thing for 2. Well, isn't the same thing going to happen? Get a negative signed area, 1/2 times base times height. This time it's a negative 4. Let me show you my work at this point. So you see what's going on. When they want to know what happens at x equals 3, you put a 3 there. You get a new triangle. That signed area is negative 9. And then, where's my graph? That works just great down to this far. But then when we go over to 4, it's not a triangle anymore. Okay? So how about this? How about taking the red signed area, finding the blue signed area, and adding them together? Won't that give me the signed area of that new region? So that's what I did. Okay, so to get the integral from 0 to 4, I wrote it as the integral from 0 to 3 because I already know what that is. I found it just a minute ago. Plus the signed area from 3 to 4. Does that make sense? So that's how I come up with that. And then to get when x equals 5, that's the integral from 0 to 5. Again, I'm going to piece it together. I've already got that. Now I need to find that and add them together. Okay? So take the answer you've already got as the integral from 0 to 4, figure out what the integral from 4 to 5 is, add them together. And then I kept doing the same thing. The integral from 0 to 6, at that point I knew what it was from 0 to 5, find the area from 5 to 6, add them together. And to get the integral from 0 to 7, at that point I knew, well, at that point I need to be careful. So let me back up. From 0 to 5, that's where my negative signed areas are going to be, right? No matter how I set that up, and the whole thing, negative signed area. Once I 5, now what's happened? Now positive signed areas, correct? So I decided that for me, it made sense to just keep the 0 to 5 as the negative signed area, and then just add on positive signed area. Okay? So that's why I kept that one from 0 to 5, and then from 5 to 7. Then, I don't know, I guess I mixed and matched then, didn't I? Then I went 0 to 7, 7 to 8, 0 to 8, 8 to 9, 0 to 9, 9 to 10. Does all that make sense? Everybody can do that? All right. So then we need to answer the question. So I've got my little chart here. They ask me on what interval is little f positive? The little f was 0 at 5, and then everything to the right of 5 is positive. So you can either just write x greater than 5, or you can make an interval. It needs to be open at 5, because it's not positive when x equals 5, right? Or t equals 5, actually. X equals 5. But it's 0 at 5. So to the right of 5, well, where was it negative from 0? Where is capital F? Well, by looking at the chart, capital F is increasing. The smallest it got was negative 15, then it started picking up. So it's increasing from 5 to 10, and then it was decreasing. If you notice, from 0 to 5, it kept getting smaller. And then let's stop for a minute. Didn't we say that little f was the derivative of big F? When the derivative is negative, the function is decreasing. So when little f is negative from 0 to 5, its function, capital F, is decreasing. Then to the right of 5, from 5 on, little f is positive, which means the function it's the derivative of is increasing. That always goes together, right? Negative derivative, function decreasing. Positive derivative, function increasing. All right, and let's see. Then they want us to plot those points and make a graph. That's what I did here. Okay? And then how you smooth it out, I mean, who knows, right? You just smooth it out the best you can. So it looks something like that. And then they ask us, on what interval is little f decreasing? Well, okay. Let me see, how am I going to explain this? All right, I'm drawing a blank. Help me out. Oh, concavity. Concavity. Okay? When the function is concave down, the function, this is the graph of capital F, isn't it? All right, we plotted the points, x, capital F of x. We're graphing capital F. Look, capital F is concave down. Concave down means the derivative is decreasing. So when that function is concave down from 0 to 3, little f, the derivative, is decreasing. And then when is little f increasing? When capital F is concave up. So concave up, concave up, concave up, that far. Okay, actually, since it's then concave down from, and again, I'm kind of hoping I drew it right, you know what I mean, when I smoothed it out. I didn't address what happens between 7 and 10, did I? Since it's concave down again, I should have said that f is decreasing from 7 to 10 again, shouldn't I? Because I was back to concave down. Okay, I just left that off. So then they ask, when is the graph of capital F concave up? Well, we already answered that question to answer when little f was decreasing. I say up. Down is obviously what I meant. And then when is capital F concave up? We already answered that when we said where little f was increasing. And again, I, for some reason, left off the 7 to 10. And then what's the relationship? Little f is the derivative of capital F. All right, so I felt like I was scattered all over the place. Did I explain that one okay? Sometimes I get twisted around when they're trying to play like we don't know that's the derivative, but we do know that's the derivative. You know? All right. Anything else from worksheet 1? Okay. I'll bet you know I want you to do worksheet 2, don't you?